Okay, welcome to this episode on unconditional diffusion of images in low resolution. It's a practical episode where we go through more detail of the DiffusionFastForward framework. We look into the code, and hopefully that will give you the right idea of how the framework is structured, so you can navigate the code more easily and maybe experiment with diffusion. We'll also go through a Colab notebook where you will be able to train and generate images in low resolution yourself. Okay, so let's start with the framework structure. We first have a pixel diffusion PyTorch Lightning module. So that's the highest level module implemented in Lightning, just so we have this useful functionality for training our network. And inside that module, we have a denoising diffusion process PyTorch module, which basically combines three crucial components: the backbone, which is the architecture, the neural network architecture responsible for predicting epsilon noise in the input sample. We have a forward model that allows us to generate samples at any given temporal index with added noise. And finally, we have a sampler. And this sampler can make use of the backbone architecture to generate new samples, but we can actually use many different samplers as once we have trained our network to predict epsilon reliably. Okay, we'll be using the DPM for most examples here, but the key idea here is that we can actually use a different sampler if we want to, and maybe get different results. So that's why we have this type of structure. We have backbone, forward model, and diffusion sampler contained in the denoising diffusion process PyTorch module, and that's contained in a PyTorch Lightning wrapper for our convenience. Okay, so first up, we will discuss the schedule. Schedule is a bunch of variables that are quite useful for computing the diffusion, certain diffusion operations. Certain operations within the diffusion process. In this case, we have a schedule of 1,000 time steps. It's a linear schedule. I think we have implementations of multiple schedules in DiffusionFastForward. For most examples, we'll be using a linear schedule. And then we have quite a few derived variables, but they're all quite easy to compute. It's just a lot of useful constants that are good to have at the disposal during the diffusion process. Normally, we register these as buffers, so that allows us to restore these. Basically, we will have these variables will be restored when we save and load a PyTorch module. Okay, and at the same time, they won't be treated as parameters that should be optimized during training. Okay. So next we have the denoising diffusion process, which will combine all these three elements. So in our initialization, we have some parameters such as the number of generated channels, the type of loss function, the number of time steps in our forward process. But then the most important components are here, the three crucial bits, which is the forward process, the backbone model, and a sampler that we will be using by default. Okay, so sampler is only useful for generating images, and later on you can actually change it to some other sampler. So I would guess that two first elements are slightly more important than the third one. The third one is maybe the default sampler that will be used if you just want to generate some samples. Okay, so inside the same module, the denoising diffusion process, we can define a p-loss, which is basically what's being optimized during training. And again, as similar, I think, to one of the previous examples in the earlier episode, we use we sample T uniformly, and then we use a forward process to get our output noisy sample and the noise shape epsilon. And we try to predict epsilon, and we use our loss function to compute the error. Next is the forward. So what forward will usually do is actually trigger the full sampling loop to generate a new sample. So I thought it would be quite convenient to just call the denoising diffusion process to actually generate a sample rather than do something else. So it actually goes through the full inference cycle. So there's a range of time steps. It reverses that. So we go from the very last time step to the very first. We start with a random xt sampled from a pure Gaussian distribution. And then we use our sampler to step through the reverse process. Okay. So that's the denoising diffusion process. The forward process is we can actually use many different forward processes as well, but most often we use Gaussian diffusion. So in this case, it will be a Gaussian process. And if that's the case, we will overload the forward and step functions. And the crucial part here is that we use some of these variables pre-computed based on our schedule. We sample the mean and we sample from the Gaussian distribution parameterized by the mean and STD, and mean is basically dependent on the x0. So basically in this function, we want to go from a clean sample to a sample at a given t. But very often we want to return noise as well, because noise is essentially epsilon. Noise is sampled from a pure Gaussian distribution. That's the target of the network. So when we actually have p-loss, like in the previous example, right here, when we have p-loss, we want to actually, this noise is the ground truth, right? And noise hat is the network output. So that's why it's quite useful to return this noise within the forward process. Similarly, we also have step. It's not used as much because step basically allows us to step one step at a time to diffusion rather than go from clean sample to any stage of diffusion. Okay, so that's that. There is the sampler as well. Sampler allows us to predict the next step of diffusion. Okay, so based on xt and noise vector zt, so that's basically the epsilon approximation. It basically returns a sample from the distribution from the previous step. And if we do that many times, we can actually progress through the entire chain of the reverse process. The crucial part is the posterior params, and these posterior params, again, these follow the equations that have been featured in the previous episode. But basically, the mean is based on the noise prediction, and the noise prediction is basically predicted by the network within the denoising diffusion process rather than a sampler. Okay. So that was the DPM. Finally, the PyTorch Lightning module. There's not that much left to do because a lot of stuff is just going on inside those submodules. So in the training step, we call the p-loss, and we try to minimize that. But what's quite useful is the input t. So generally in the denoising diffusion, we will expect the samples to be in -1, 1 range rather than 0, 1 range. So we can actually, what we can do is define our input transform and output transform. When we want to compute the loss on our images, we use the input transform. But then when we generate, we actually use the output transform. So when the model generates something that's in the -1, 1 range, and when we want to display an image, we usually want it in 0, 1 range if it's a float. Okay, so that's the Lightning module. Now, I think we've gone through the majority of the framework. There's a training notebook that you can find on the course website. I will I think I will open that in a minute in this episode as well. If you use that, if you train for about 200,000 steps in 64 by 64 resolution, the data set that we will be using is a maps data set from Pix2Pix paper. And you can get these types of results after roughly 9 hours. So that's 200,000 steps with a batch size of 16. And that's been done on a Colab, on Google Colab. So you can do it for free in your browser. Now, if we go above that, you start to generate some samples, but it's much more difficult to converge. It takes more time, and generally you will go over the limit for Google Colab. So if you have your own server, if you have your own machine, you can actually train this higher resolution, but you need to be more patient. But for something that's 64 by 64, you can get something reasonable in less than 10 hours. Okay. So next up, I will go through the notebook. I will show you where to access it and how to run it. Okay. So that is the DiffusionFastForward website, where you can access all of the materials, including these videos, the notes, and all of the code. The code is here in the main directory, but if you follow the README, you can actually access all the notebooks in Colab. So what we're going to do is actually open the Colab for Pixel Diffusion and run it. Okay. So first of all, we want to make sure we have the right type of runtime. We want a GPU acceleration, otherwise we won't get very far with training, okay? So we save that. We wait a little bit to connect to a server. So first thing we do is clone our repository, install some crucial libraries for running the code. And then we'll download the dataset, and it takes a few minutes to download it. Okay, almost there. The final countdown. And our dataset of maps from Pix to Pix will be downloaded. Obviously, if you run it on your own server, you can just download it once. If you run it on Colab, it will be part of the experience, I guess, but it's only 2 minutes, and then you can crack on. So that's our simple image dataset for the sake of this experiment. We'll have a crop size of 64, and once we go through those cells, we get a bunch of samples from our dataset. That's what real samples look like. They're quite low quality anyway, so our model has managed to train something that's quite similar. Then we just instantiate our model for Pixel Diffusion. We set up our trainer, and we kick off the training, okay? And that has to train for quite some time. So we want to wait about 6-8 hours at least to get something reasonable. And once you do that, you can then use the sampler, be it a DDPM sampler or the built-in sampler, okay? So here, in the first instance, in this example, in this cell, we're actually using the default sampler, which is DDPM. But as we show, we can also use DDIM to sample faster. But we're getting ahead of ourselves, because I will be introducing DDIM in one of the later episodes. So that's it for this practical episode. I hope you enjoyed it. If you want to stay for conditional diffusion and high resolution diffusion, I recommend you check out the subsequent episodes of this course. Okay? Cheers.